Let's consider an ideal spin system with capital N spins. So we can label these spins as number 1, number 2, number 3, all the way up to number N. Etc. So these are ideal spins. There is no interaction between the individual spins. There is capital N number of spins in the system. They are, since it's an ideal spin system, they are statistically independent, and when we have no external magnetic field, probability of a spin being up or down is 1/2. So this is what I recall from our previous discussion, and I call N number of up spins, and I call N prime number of down spins, and I have the net number of up spins, total magnetic moment number, N minus N prime, which is N minus capital N minus M. We have shown this to be 2N minus capital M. That's the total magnetic moment number. That's the net upspin number if the moment and the spin directions are parallel. Each spin has a magnetic moment associated with it. Magnetic moment is either plus mu 0 or minus mu 0 for the spin orientations, and the total magnetic moment is then equal to the net number of up spins times mu 0. So that's basically, I'm saying, if a spin is up, the corresponding magnetic moment is plus mu 0. If it's down, it's minus mu 0. So it's a positively charged particle that has a spin. So this is basically given by 2N minus capital N mu 0. So what are the possible values of N? Well, N can take values, no spins can be up, 1 can be up, 2 can be up, all the way up to capital N. The corresponding values of the total magnetic moment would be, if N is equal to 0, you can see I can start from minus N mu 0. If N is equal to 1, it would be 2 minus N mu 0, 4 minus N mu 0, capital N mu 0, all the way up to, for N, capital N minus 1, it would be capital N minus 2 mu 0. When N is equal to capital N, 2 capital N minus N, this would be capital N mu 0. These are the possible values capital M can have. So that's basically a discrete variable. And because I have this relationship, capital M is equal to the net number of up spins times mu 0, the probability distribution for capital M is the same as probability distribution for M is the same as probability distribution for N, because M is related to N with this 2N minus capital N, and M is related to capital M with this expression. So I have this relationship between the probability distributions being the same. So if you look at this distribution in detail, you can see that if I'm close to the mid values for capital M, so close to the average value of capital M, that is basically somewhere in this range here, the variation of the probability distribution becomes less and less important, especially if I'm really close here. You can see that it's almost a constant. So basically, what I notice is that for a large number of spins, for large n, large capital N, except at the extreme values where m is equal to minus n mu 0 and plus n mu 0, the variation is a slow variation. So whenever I have a small interval dm in which I'm looking at the variation in the probability, it's going to be rather small. So the probability distribution m does not vary a lot. Does not vary a lot. If I'm far from the extreme values, for m far from plus or minus n mu 0, the extreme value. So there I have a relatively large variation. Okay, and how do I calculate this probability distribution? But basically, what is this plot that I have here? Well, this plot that I have here is just p double prime m, which is the same as the probability distribution for total magnetic moment number, the same as n, which is the combinations of capital N objects taken n at a time, p to the n, q to the n prime. It's the binomial distribution. Okay, so how important is it to show this discreteness of the values in this distribution? I'm going to demonstrate this with an example. Let's consider, for an example, capital N is equal to 10. So I have 10 spins. And I want to be relatively close to the middle of the distribution. So what is the probability of having 6 up spins? It is 10 factorial, 6 factorial, 4 factorial. If the external magnetic field is 0, the probabilities are 1 over 2 for up and down spins, 1 over 2 to the 4th power. This, if you calculate, is 210 divided by 2 to the power 10. And if I calculate probability of having 7 up spins, it would be 10 factorial, 3 factorial, 7 factorial, 1 over 2 to 7, 1 over 2 to 3, and this would be 120 divided by 2 to the power 10. So how much is the variation in the probability going from 6 up spins to 7 up spins? It is 90 divided by 2 to the power 10, which is a rather small number. So this is small variation. So I realize that as the delta p goes to the a large variation in probability becomes a small variation in probability as capital N increases. You can see that this capital N is entering this calculation at this point as a power of 2. So if I have 2 to the power Avogadro's number, if n is of the order of Avogadro's number, then this delta p would be a constant divided by 2 to the power Avogadro's number, which is very, very small. So it's an incremental change in the probability. So as n increases, the discreteness of this probability distribution of the binomial distribution in this case becomes less important. This is an important conclusion that I obtained from this calculation. So basically this will allow me to replace this discrete distribution with a continuous distribution you can see here. And basically in this case I will have the following question: what is the probability that the total magnetic moment is in a range m to m plus dm? And the answer will be given by the probability distribution function multiplied by the range of values dm. So with the assumption that mu 0 is sufficiently small, such that any dm I consider of interest is going to satisfy dm much greater than mu 0. So basically you will remember that the discreteness of m, so for the difference between m values is given by 2 mu 0 here. So it's discrete in units of 2 mu 0, and therefore any range that I pick must be much greater than mu 0, so that the discreteness is not important. But the dm value that I'm choosing should be also much less than the maximum or minimum magnetization values, absolute values, so that we can write the following. The answer to the question: probability that the total magnetic moment is in the range m to m plus dm. So this probability is the probability density function Pm multiplied by dm. So this is the basically turning the discrete distribution into a continuous distribution by picking up a range that satisfies the condition that the discreteness is insignificant. So here we call this function Pm is called the probability density function. Okay, so how am I going to find this probability density function? So let's think about this process here. I pick a certain value, so let me plot this distribution on a sketch here. So I have this distribution, and here the m values are discrete, but basically I'm picking a range around m bar, let's say. So here I pick a value m0 and this is a value m0 plus dm. So I would like to know the probability of finding the total magnetization in this range. So if I think about the discreteness of this process, let's say that the possible m values are actually placed like this. So I have many different discrete m values in this range, and therefore if you ask me what is the probability of finding m in this range, that means m can have a value m0 plus delta m, and then m can have a value m0 plus 2 delta m, etc., all the way up to m0 plus dm. So the answer to this question, considering the discrete distribution, probability of m in the range m0 to m0 plus dm will be given by the following. The probability of finding an m value m0 plus delta m plus or finding the next possible discrete value 2 delta m, etc., all the way up to the probability of finding m0 plus dm. Okay, so here the assumption is that basically when I concentrate on the corresponding probability values, they are very close. Okay, so basically I replace this probability distribution function by choosing a small enough range with this. So I say that, well, this is the probability value for all numbers, m numbers in this range. So basically I will have the following situation. I will have probability of finding a value at m0 plus probability of finding a value m0 plus probability of finding a value m0. How many times? Well, it is basically going to be equal to probability of finding the value at m0 multiplied by the possible number of m values in this range. And what are the possible number of m values in this range? Dm divided by delta m, where delta m is the unit of discreteness. So this delta m we have found to be 2 mu 0. So basically that's going to be the answer. So because the question of probability of finding m in a range is basically the same thing as saying what is the probability of finding a value m0 plus delta m or m0 plus 2 delta m all the way up to m0 plus dm. So this is basically the either or situation that we have considered before. So we adopt the probabilities, and with the approximation that the probability distribution does not vary much, I just take the value, the initial value, and multiply it with the number of possible values. I get my answer. So if I have dm much greater than delta m, which is 2 mu 0, then basically I want my answer to be this probability distribution function times dm. So this is going to be equal to the same thing I have calculated here, because these are the probability values, discrete probability values. This will be equal to probability of finding the m value multiplied by dm divided by delta m, which is 2 mu 0. So these two should give the same answer. So that's how I find the probability distribution function. And if dm is 0, I should note that if dm is 0, that means there is no range, the probability should be 0. Alright, because the first number that I pick is not one of those discrete values. So basically this probability distribution function as a function of m multiplied by dm, that's the probability of finding the m values in this range, m to m plus dm, is going to be something multiplied by dm basically, and we can show by using this relationship here, we can show that for large m values, for large m, which is capital M divided by mu 0, which means m is not close to 0, or actually we also don't want it to be close to its maximum value. This distribution, n capital N factorial, n factorial, capital N minus n factorial, p to the n, q to the capital N minus n, can be replaced with this distribution, 1 over square root 2 pi capital NPQ e to the minus n minus np squared divided by 2 npq. This distribution is known as Gaussian distribution. We're going to show this in the next video, that we can replace this discrete distribution with the probability density function given by the Gaussian distribution. Now what I want you to realize about this Gaussian distribution is that it can be written in this form, 1 over square root 2 pi, the standard deviation of n, exponential minus 1 over 2 n minus n bar, deviation from the mean value, divided by standard deviation square. So here we have the mean value, capital NP. The standard deviation of n is square root NPQ, as we have shown previously. So that's the form of the Gaussian distribution. So in general, we can generalize this for a continuous variable. So for a continuous variable u, the probability of having values in the range u to u plus du is given by the probability distribution function multiplied by du. This function is the probability distribution function, PDF. Okay. So let's say that for a specific case, if u can take values in a certain range, only in the range a1 to a2, let's say, then if I calculate the probability of finding the u values in this range, probability distribution function du integrated over all possible values, this must be equal to 1. That's the normalization condition. And if I have any function of u, if I want to know its average value, I need to go over all possible values of u, multiplied with the probability distribution function f of u du. So this is basically generalizing the ideas that we have introduced to continuous variables that are in a range. And another generalization, if I have two variables, two continuous variables, u and v, the probability of u being in the range u to u plus du and v being in the range v to v plus dv is given by the joint probability distribution function puv du dv. So this is puv is the joint probability distribution function, and we have seen if these two variables are statistically independent, it would be equal to probability distribution function of u multiplied by probability distribution function of v, but that requires them to be statistically independent. Okay, so let's summarize what we did here. We have shown, using the ideal spin system, the total magnetic moment m takes discrete values, and it can take values from minus capital N mu 0 to plus capital N mu 0 in units of 2 mu 0. And because of the relationship between capital M, lowercase m, and lowercase n, the number of upspins, total magnetic moment number, and total magnetic moment, they have the same form of the probability distribution, which is the binomial distribution. Now I realize that the discreteness of this distribution can be ignored if the unit of discreteness, 2 mu 0 in this case, is much smaller than a range that I'm considering, a range dm that I'm considering, but this dm should be taken sufficiently small that the variation in the probability in this range is can be approximated by a constant value. So that's what I have done later on. And in order to show that this discreteness becomes less important for increasing large n values, I have taken n equals 10 as an example. You can see that variation in the probability is as something divided by 2 to the power 10, which is small. For a very large number, like Avogadro's number of spins, this would be a really, really small variation in the probability. So it is becoming less and less important as the number of the spins increases. So with the assumption that this discreteness mu 0 is sufficiently small for any range of interest that I consider dm, what is the probability of the total magnetic moment being in the range m to capital M plus dm? That is given by probability distribution function multiplied by dm. And how do I go from a discrete distribution to a continuous distribution? Well, you need to consider for the range of interest the possible values of capital M and their corresponding probabilities. Now, if this range is taken small enough and if it is sufficiently close to the center of the distribution, especially, you can basically, to a good approximation, say that the probability of each discrete n value in this range is the same as the probability of finding the first possible value in the range. So that's Pm0, and then for the next one, it's the same because the change in probability is negligible, and all the way up to the dm values, the dm range divided by this unit of discreteness to mu 0. So because the probability distribution function will give the same answer, basically probability distribution function is the discrete distribution function divided by 2 mu 0, divided by the unit of discreteness delta m. If the range is 0, the probability should be 0. And we can show that for large m values, and when you have large number of spins in the system, the binomial distribution can be replaced by Gaussian distribution, which has the form 1 over square root 2 pi standard deviation exponential minus 1/2 deviation from the mean divided by standard deviation to the power 2, where the average value for n we have found previously to be capital NP, standard deviation square root capital NPQ. Now, if I have a continuous variable u, so I'm generalizing this discussion, which can take values only in a certain range, a1 to a2, then if I consider the probability of finding all possible values in this range, a1 to a2, it should be 1. So integral a1 to a2, probability distribution function du should be 1. And for any function of u, finding the average means you have to multiply it with the probability distribution function and integrate over all possible values to get the average. If we have, on the other hand, two continuous variables, u and v, the probability of finding u in a range and v in a range is given by the joint probability distribution function du dv. The joint probability distribution function will only be equal to the product of the two distribution functions p of u and p of v when these variables are statistically independent, as we have shown in the previous